right? We have our three most fundamental pieces. Resources are finite, change is continuous. There are other players in our systems who are adapting too, even as we adapt in order to achieve growth and to handle challenge. Now, what that means is there's a few requirements on capabilities. Synchronization is necessary across adaptive units in the network. The network is a tangled, layered network. Different units who engage in adaptive behavior. Units of adaptive behavior is the neutral language we will use, or shorthand, adaptive units. Adaptive units have a range of adaptive behavior, right? They can't do everything. Resources are finite, change is continuous. So we need to be able to synchronize the activities in different ways at different times across those units in order to produce better capabilities, more performance, to shift where we are in the network of trade-offs. So across those dimensions, we may need to synchronize differently depending on the pressures and how that we need to adjust our position in the trade space. The second, synchronization is important because it relates to one of the three basic ways that adaptive systems can break down. Adaptive systems can malfunction. There are three ways that adaptive systems malfunction. One of those is at the synchronization level, right, of how multiple units interact and coordinate to achieve more, right, rather than destructively interact or constrict each other when they're under challenge and pressure. That's the risk of working at cross purposes, right? Behavior at one unit that's locally adaptive for the position of that unit in the network, but globally maladaptive with respect to a region of the network and the goals that it's trying to achieve. In effect, I have a conflict between what is locally adaptive for one unit, right, the goals that govern its performance, and the goals of the neighborhood of the network that unit of interest is embedded in. So from a neighborhood level, right, the goals are different, yet partially aligned, yet not completely aligned, so that we can get working at cross purposes as one unit emphasizes achieving their goals under pressure and risk, right, but does it in a way that undermines the ability for other interdependent units to achieve their role, supporting the goals of the region or neighborhood of the tangled layered network. Now, a second necessity in our network of adaptive units is we have to have mechanisms to offset the risk of saturation. And we'll talk quite a bit about saturation as a problem, or its inverse, the capacity for maneuver, right? How much capacity for maneuver remains as I have to carry out an activity under stress, under pressure, as change increases the pressure, as variations increase the disturbances that I have to that I have to overcome in order to regulate the key goals, the key parameters I'm trying to achieve in whatever role I am acting in. The risk of saturation is a universal, and the need to regulate my capacity for maneuver, my remaining or my future capacity for maneuver, right, is fundamental to having extensibility. So we have to be able to monitor the risk of saturation and act effectively in the face of that risk. Now, we'll explain that more because this turns out to be quite basic in engineering. In control theory, dynamical systems, it turns out that saturation and delay are critical parameters that undermine our ability to act effectively in controlling dynamical systems at any scale and of any type. And so understanding how this works is going to be very important to us in understanding both the fundamentals and the actionable pragmatics that make our understanding of adaptive capacity turn into the ability to engineer resilience in our systems. Now, the form of breakdown of adaptive systems that this is related to is called the risk of decompensation, the failure to keep pace, an inability to decide on and act, take actions to effect as situations deteriorate. As they continue to deteriorate, can I keep pace, interjecting effective counteractions, right, to offset those disturbances, eventually to not just mitigate them, but to stop whatever is the driver producing those disturbances and disruptions in the process I'm trying to control. So the risk of decompensation will explain that and illustrate that more, whether at the level of, for example, your cardiovascular system and how that manages the risk of decompensation as the cardiovascular system comes under different loads or different levels of stress. Or we can talk about it in terms of controlling a parameter, controlling an airplane. We can talk about it at much higher layers as we explore different scales of systems, organizations, and societies as we think about resilience. But all of these are operating dynamically. Change is continuous. They have to keep pace with change. And we'll illustrate this, right, in how we try to achieve growth in the face of constraints as well.